Okay, we'll start the lecture. All right, so today, today's lecture is about sequences and mathematical induction. So first, we will look at what sequences are, some components, main components of sequences, and then different types of sequences along with some notations. Two of them we will discuss, summation and product, and their properties also. Okay, let's start. Okay, so we'll start with an example. For instance, you want to you want to count, let's say you want to count your ancestors, and you start from your parents. So you have two parents, mother and father, and then each of them have two parents, and then each of them have two parents, and so on. So this, when you look at the pattern of these ancestors, you can first write it in the form of this tree. You can write it in the form of a sequence. Okay, so this is your parents, and then these are the grandparents, and then their parents, and so on. So you will observe a pattern over here, which you can write in the form of a sequence. So in a sequence, you have a consistent pattern that repeats in the terms. Okay, and each value, this is known as term in a sequence, and each of the term in a sequence has a position. For example, if we talk about the sequence that we just talked about, I gave you an example of, which is your ancestors. So you can see that the two, which is your parents, they are at position 1, and then 4 is at position 2, 8 position 3. So it means this is just to show you that each term in a sequence has its own position. Let me let me record it actually. Okay. All right, so we were talking about sequences. For example, in the sequence of ancestors, the number corresponding to position 1 is 2, and number corresponding to the position 2 is 4, and so on. To position 3 is 8, and so on. So each sequence, each term in a sequence has its own position. And if we look at this particular example of the sequence, we can say that this is power. The first term has power 1, second term has we can write it in the form of the power of 2's. This shows you a pattern, okay, over the terms. So this is what I just told you, that each sequence has a specific pattern that repeats consistently over the terms, starting from the initial value till the final value. Okay, so this ancestor one, how we can write it generally, it's similar to the concepts that we covered in your predicate logic, that we have a general formula. For example, for even integers, we have a general formula, which is this 2k, and then for odd, we have 2k plus 1. When we plug in any integer value over here, we will get the value. So this is a general formula. Similarly, for the sequence, we also have general formulas. For instance, to count the number of ancestors, we can write it in the form of a sub k equals to 2 to the power k. Because if you look at this pattern, you see it is consistent pattern of powers of 2. Okay, so here this is consistently changing, so that will be k, and then this is how we represent it, a sub k. Now the term over here, let me go down. Okay. So how do we read this? We read it as a sub k. Here this k is the index or subscript. That is why a sub k from the subscript. Okay, and then 2 to the power k. So that is an example of a general formula for a sequence which tells you about the a pattern that is present in a particular sequence. Okay, so that is what a sequence is. I will go through the formal definition of sequence. So what a sequence is, it is a function whose domain is either all the integers between two given integers or all the integers greater than or equal to a given integer. What does it mean? That here in discrete structures, mostly we deal with integers, okay, whole numbers. Okay, we do have real numbers and some other types of numbers, but most of the times we deal with integers. So a sequence, it's a function, the domain of which is either, let's say, some, for example, 4 and 8, that is given to you. This is what means by the first part of the definition of sequence, that either it is a function whose domain is either all the integers in between two given integers, or it is greater than or equal to some given integer. Okay, so that is what a sequence is. Is it clear? All right. Now, term I have already told you. We typically now how to write down a sequence regardless of what pattern is available or present in the sequence. How do we write it? We typically write a sequence as a set of elements. So elements are the terms in a row. Okay. So for example, our initial term in form will be a to the power, sorry, a sub m. How we read it? A sub m. Then second term can be represented with a sub m plus 1. Third term with a sub m plus 2, and then up to some final value. Oh, sorry, this is not plus, but n. Okay, so this is the final value, or we also call it as the upper limit, and this is your initial value, or we also call it as lower limit. This is the general representation of a sequence, okay, written in a row. When we don't have a final value, and let's say our sequence looks something like this, without a final value, ellipsis, and this is known as infinite sequence. Usually we deal with in your mathematical induction and in sequences, generally we deal with some particular terms or values in a it is enclosed in a range. Okay, so we have some final value. All right. Okay. So I'll go through the information over here. This is the same as what I have told you, that each individual element represented with a sub k, how do we read it? A sub k, it's called a term. So this is first term, this is second term, this is third term, and this is your final term. The k in a sub k is called a subscript or an index, the same thing. And we can define it with m or any other variable. It could be an integer. It is the subscript of the initial term, and n is the subscript of the final term. This notation is known as the infinite sequence. And for every sequence, we have an explicit formula or a general formula. What does it mean? That we have some formula where when we implement or we plug in any integer, we will get the value for that. So we have some established explicit formulas for some well-known sequences like Fibonacci sequence, and then sum of first few integers, and sum of geometric sequence. So we have a lot of sequences for which we have explicit formula. So we can also find out explicit formula, or we also call it as general formula or closed formula, based by analyzing the pattern that is available or that is present in the sequence. Okay. Okay. Now, different types of questions, just like your previous lectures, what type of questions you can expect in your final exam from these topics. We will go through those. So, one type of question that you might get from the sequences is that define sequences. Some sequences are given to you, and explicit formula for those sequences is also given to you. And then you have to compute some terms. First, maybe like first 5 terms, first 6 terms, first 7 terms, and so on. So there you have to look at what information is given to you, sequence is given to you, explicit formula for each sequence is given to you, and initial value is given to you from where you will start. So always we have some initial value. We need to have some initial value to start finding the terms, further terms in the given sequence. For example, if this type of question is given to you, and then you have to compute, for in this particular example, you have to compute first 5 terms of both the sequences. What you will do is that you will look at the explicit formula, then you will see what the initial value is given to you. You will start from there. So the initial value, the smallest value, that it's 1. So wherever you have k, you will plug in that initial value and then compute that term. So this will give you 1. And then after that, you have to find, this is your first term in the sequence, in this sequence. Now you have to compute 5 terms. You will apply the same formula, just that after your initial, you will look at what is the next integer. So you will plug in that in k. So next value after 1 is 2. So plug in that wherever you have k. Okay, plug that in. And whatever value you get. Okay, after that you have next one is 3, because you have to find out 5 terms. So this is your first term, this is second term, and then you have your third term, then you will have fourth term, and lastly you will have sorry, I don't have space, so I'm writing it over here, but you have the solution in the next line, so you can go through that. And then this is your fifth term. So this is how you find out the terms based on the information given to you in the question. Okay, if you look at the solution, you will see over here, sorry, this is 1 by 2. So this is how this is the same. This one we computed first term, second term, third term, fourth term, fifth term in a given sequence. So how you can write, now you have found out the first 5 terms of the first sequence, which was this one. How you can write it? Just take the terms and write them down separated by comma. Is it clear? Just write in chat box if you have any question. And if it's clear, then just you can write it down in the chat box. Okay. Same is for your second sequence. The formula over there was I minus 1 divided by I, and initial value was 2. So it means that you will start your finding the term from starting from 2. So first term will be I minus 1. You will plug in 2 wherever you have I. Okay, so that will give you your first term. After that, after 2, next integer is 3. So write that down, and that will give you your second term in the second sequence. Then third integer after 3 is 4. So plug that in, and this will be your third term, and so on. So this is fourth term, and then fifth term. So this is how you find out the terms in a sequence that is given to you, given that you have the explicit formula for that and initial value. Is it clear? Sequence topic, okay, this question, sequence topic is about computing and also about different types of notations that this will form a base for you. You will find these in your mathematical induction. So that is why you need to know this information. It's not only about computing the terms, this is take it as a foundation for your mathematical induction. Yeah. All the concepts. Clear? Any other question? I'll wait for 2 to 3 minutes. If you have any questions, you can write them down in the chat box and I'll answer those. Okay, next topic, we'll move forward. Here you have one example. If you look at this formula, explicit formula, and when you try to compute the terms by plugging in the values, you will see that when you get 4 to 5 values, you need to analyze at least 4 to 5 terms to check whether the pattern is consistent or not. The pattern should be consistent for there to be a sequence. Otherwise, you cannot have a general or explicit formula if the pattern is not consistent. It's not the same. So if you look at this explicit formula and you compute first few terms starting from 0, so there -1, and then first wherever you have j, you will plug in the smallest value. This will give you first term. Second term will be next integer after 0, 1. Third term will be next after 1. Next will be after 2, it's 3. And let's look at first 5 terms in this formula. So when you compute this, when a number has 0 in its power, in discrete math, we take it, or discrete structures, the value for that is 1. Okay, so it will be 1, and then -1, it will remain as -1. -1, this one, it means -1 into -1, so it changes to 1. Then fourth term, it is -1 into -1 into -1, so answer is -1. Fourth term is -1 multiplied, you multiply it 4 times, so you get 1. And then lastly, let's look at sixth term as well, that you will get. It means that -1 is multiplied 5 times, so you will get -1. So here, if you see, it is an alternating, the terms tell you that it is an alternating pattern of 1 and -1, and this pattern is consistent. So that is why you have this formula for the sequence, which is this. This is the sequence that you found out, that you can compute by plugging in the values, and this sequence has this formula. Okay. So you can determine the relationship between the explicit formula, and you can find out the sequence. You can look at the pattern over 4 to 5 terms, and then determine whether that explicit formula is actually for that sequence or not. Okay. Okay, question is, so whatever value indicated at the unknown variable will be brought up to the question. If I understand correctly this question, yes, you will be given, if you have this type of question, you will be given an initial value, because you have to start from somewhere. So if you don't have, for instance, please give me 1 minute. I'll be back. Okay, so to answer the question which is posted in chat box, either you are given the initial value, or let's say it is not mentioned in the question. For example, here in the question it is mentioned, this initial value is mentioned, right? So you know what will be your starting point. Let's say it is not mentioned, but still there will be something, for example, positive integers, okay, something like that. So here you should know that positive integer, where does this start from? What is the smallest positive integer? That is 1. Okay, so you should know these keywords also. Either these keywords are given to you, or directly the initial value is given to you. One of these is necessarily given to you. Okay. Yeah, all right. Okay, so let's move on to next slide. Here you see it's the same thing that I showed you the example of. This one, it's the solution, so you can go through that. Now, second type of question, this was first type of question in your sequences. Second type of question that you may have is that you have to find an explicit formula for a given sequence. Okay, so here, and the sequence is given to you. Here, what you need to do is you have to analyze the sequence. You have to some terms are given to you. See, 1, 2, 3, 4, 5, 6 terms are given to you. So 5 to 6 terms are given to you, and you are asked to find out explicit formula, general formula, and closed formula. It's the same thing in the context of this lecture. So this is your job to analyze this the sequence in the terms, and then design a formula for that, such that when you plug in any integer there, you will be able to get these terms. Okay, so here your analysis your analysis capabilities are important. So if you look at, for example, this one, this first term, second term, third term, fourth and fifth and sixth. So if we focus on the numerator first, you see, you will find a pattern over here. You have alternating sequence of 1 and -1. So in the numerator, initially you can write it as plus -1 like this. Now if we focus on the denominators, this is just one example of a sequence. Okay, you see, if you look at the pattern, you can observe that these are perfect squares of integers. Okay, so you can write them down as k square. Okay, so whatever number you write over here, you will get the value. For example, if k is equal to 2, if you plug that in over here, you will get the value. Okay, if you plug in k is equal to 3, if you plug that in, you will get the value. So this will be your initial deduction, but then you have another. Now you can try to find out a relationship between numerator and denominator. So you see, wherever you have -1, there you see in the denominator the square is of even integers. Okay, so you can further refine this formula in a way, because you cannot have +1 -1 like this, 4 and +1, because this formula, this will give you values in this format: +1 -1 over 4, +1 -1 over 9, +1 -1 over 16, and so on. But what you need, so this is wrong. You need to have -1 over 4, then 1 over 9, then -1 over 16, like that. So it means that you have to further refine your formula. How you can do that? Here, the solution is given to you. If you write it like this, so you have to manipulate the numerator further, and your denominator will remain the same. Now when you plug in the values, any values, let's say k is equal to 2, if you plug that in over here, wherever you have k, plug that in, 2 plus 1 and 2 square, it will give you -1. 2 plus 1 is 3, so it will give you -1 over 2 to the 4. Then let's say k is equal to 3. If you plug that in, this 3 and then here 3, it will give you +1 and then 3 3s are 9. So you see, you are getting, with this formula, you are getting your terms -1 by 4, 1 by 9, and -1 by 16. So this is the formula that is giving you these terms that were provided to you in the question. Okay, so you this is up to you. This is what you have to analyze. You have to find out the pattern and relationship between the sequences. At least 4 to 5 terms should be there for you to analyze the pattern, and then write that down in general format, and then refine it further. Then plug in the values for k, means the integers, and then check whether you actually get these terms given to you in the question. Okay, so that is how you can find out the explicit formula for a given sequence. Okay. Okay, for this particular question is, for this particular sequence, how you reduce the formula. So how this formula is specific to this particular sequence. Okay, so this is an example given to you. So this is only for this sequence. For you may be given some other sequences, there you have to analyze, you have to find out the pattern that is present in the terms, and then you have to generalize. Okay, so for this example, I'll go through it again, because there is a question how we deduced the formula. Let's say, I'll go through it again, I'll repeat it for you. So let's say this sequence is given to you, and you're asked to find out explicit formula. You look at the terms and then try to find out a consistent pattern. To find out consistent pattern, at least 5 to 6 values should be given to you. So they should be present in the question. After that, you have to analyze that how the pattern, what type of pattern is there, how the values are changing. If the values are changing, what is the, are they changing constantly? Is there a constant pattern? So that is on you to analyze. Okay, for this particular example, if you see, we have numerator and denominator. So how we are going to analyze? We will see if there is a pattern in the numerators of the terms. you see -1 + 1 -1 + 1 -1. So you see a pattern is there. You have a pattern of +1 and -1 in the numerator. Now focus on the denominator. You see, if you look at these numbers, you can analyze that these are perfect squares, right? And then squares, how can you generally write the squares? You can write it like this, right? This could be any integer. So you can write down, you can generalize it. You can write the general variable for that. And then for square, you know that the notation for square is power 2. So that is how, this is based on the pattern that you have observed. Now, this is the formula, okay? This is where you have reached. Now, if you try to plug in these values here, will you actually get these sequences? This is what you have to check. So if you plug in, we can check. If you plug in the value of k, let's say 2, we can start from 2. Will you get the same for the second term? Will you get the same answer as -1/4? No, right? Because you are getting both +1 and -1, and then you have 4. But in originally in the question, the term is -1/4. Here in the answer with this formula that you have reduced, you have +1 -1 over 4. So it means that your denominator is okay, but here you have to further define it in the numerator such that you get -1 in specific. How you can do that? That is, you have to analyze. So you have to try. This is trial and error process. Okay. So for this particular example, if you write -1 and then if you write it like this is from trial and error process. It's not like there is no specific system for that. Okay. You try it, trial and error process, then plug in the values and then check whether you actually get these terms or not that are given to you in the question. So now once you get your refined explicit formula, plug these plug these values there in for all the terms that are given to you, and see whether this formula is applicable to all these terms, and then if yes, then it will be your explicit formula. Okay, so that is a trial and error process and an analysis. Okay. This was yeah, it's not first. Wait a minute. Let me... Yes, the question is about the first value. Yes, I was talking about second value, not the first one. Second term. Okay. So I was giving example of the second term. So two types of questions. First is compute the first few terms, where in the question general formula is given to you and initial value is given to you. Then second type of question, you have to find out, or you have to design an explicit formula for a given sequence, and in that sequence first few terms are given to you. Okay. So next we will look at two notations we will cover. First one is summation notation and second is product notation. So if we go back to the first type of sequence that I discussed, which is the ancestors, the general representation for that was this: a sub k is equal to 2 to the power k. Let's say you want to find out the total number of ancestors for some in some range, for maybe like 5 generations past, 5 generations past, 6 generations past, 7 generations. When you want to count the total number of ancestors, what you can do is you can simply add them up. Okay. So what, for example, if you have A1, this is your first generation, A2 is the second generation, A3 is the third, you can simply add them up. Okay. And let's say 1, 2, 3, 4. Let's say you have to compute the total number of ancestors over past 4 generations. You can simply add them up. Now, how you can show it? You can show it in the form of a summation. I will explain to you over here. The notation for summation is this, and a few things that you need to know about this notation is this whole sequence of sum of the terms. Here you will have the initial value, okay, whatever over here. it will be given to you in the question. Initial value or lower limit. So this is known as lower limit. This is the starting point, and here you have upper limit or the final value. This is upper limit. Okay, and this is your summation notation, and here you have the formula. For example, for this finding out total ancestors, this is the formula. So this you will have over here, and this whole sum of the terms you can represent as the summation notation. Okay, this could be 1, 0, whatever it is defined, and you start from here. Then your consecutive integers, plug those in until you reach n. Okay. Okay, those students who are facing problem in joining, are you able to join now? There might be a connection problem on your side. All right, I hope the problem is solved. Those who couldn't join, if still not, let me know. Okay. Now, how we can compute the summation notations? Let's say this type of notation is given to you. First type of question, either the values for the formula or the expression is given to you, and the lower limit, upper limit is given to you. How will you compute this? I will compute this one for you. For example, k is equal to 1. So 1 will be your lower limit. You will start from here and plug that in the expression. Okay, here 1, and then add them up. Sorry. A1 plus A2 plus A3 plus, so you have A1, next is after 1 it's 2, so A2, after that is 3, A3, so you have to reach till the upper limit, so up to A5. Okay, so your lower limit and then up to upper limit, add all of those, and then look at the question. If the values for each of these terms are given to you, simply plug those in. For example, A1 is given to you, it's -2, A2 is given to you, it's -1, and then A3 is given to you, it's 0, A4 is given to you, it's 1, and A5 is given to you, it's 2, and simply add them up, and whatever answer you get, you will write it over here. So this is one type of question. The summation notation is given to you. and lower limit is given to you. You have to start from there and substitute every k with that, and then till you reach the final one. Okay, so a1, a2, a3, a4, a5, because your upper limit was 5 over here. Same for the second one. Here, lower limit is 2 and upper limit is also 2. So what you will do is that your k will be replaced with 2. Now, if you see, it is starting from 2 and it is ending at 2. So it means only 1. You need to write down only a2. For that, see in the question, if the value for that is given to you, plug that in. Okay. That is how, this is one type of question. And also, this upper limit is usually greater than or equal to lower limit. Okay. So n is greater than or equal to m. Here, this is the general representation. Okay, so lower limit is less than or equal to n, or you can say that n is greater than or equal to m. It's the same thing. Okay, is this calculation of summation notation clear to you? Let me know in the chat box, and in the meantime I will go through the formal definition of summation notation. So if m and n are integers and m is less than or equal to n, the same thing that I told you, or you can say that n is greater than or equal to m, it's the same thing. This symbol, how do you read it? The summation from k equals m means this summation from k equals m to n, this n, okay, of a sub k, This is how you read it. So this is simply what it is reading this summation notation. It's the sum of all, what it represents, it's the sum of all the terms a sub m plus 1, a sub m plus 2 up to a sub n. Okay, so this is the expanded form of this summation notation. Okay, and we say that a sub m plus a sub m plus 1 plus a sub m plus 2 up to a sub n is the expanded form of the sum, and this is how we read it. We write it. Sorry, this is the expanded form for this summation notation. And k is known as the index of the summation notation. This is from your first slides. Index and subscript is the same thing. That is why we read it as a sub k. Okay, and m is the lower limit, this lower limit of the summation, and n is the upper limit. Okay, upper limit of the summation. Okay. Is it clear, the summation notation? Yes, summation notation is clear. You mean summation? Okay, summation is it's simply the sum of terms given to you in a sequence. Okay. I'll repeat it. So you have three things in your sequences. First is simply the terms are given to you. Okay, a sub m plus 1, a sub m plus 2, and up to a sub n. Okay, this is what we discussed in your first few slides. Then after that, let's say you want to count the total of, for example, the ancestor sequence that we covered. We want to count the total number of ancestors. We can simply add them up. So we can add a sub m, plus a sub m plus 1 plus a sub m plus 2, and then we can simply add them up, right? Now this sum of the terms, how we can represent it with this notation. sum. This is known as a summation notation. Here we have two things. This is your the symbol for summation notation, and below we have the lower limit, above we have the upper limit. This means the term for first, okay, first integer, first term. You can find out, you will start your first term from here, and then you will reach over here, you will simply add them up. Okay, this will be your upper limit, final value. Okay, this is what summation notation is. Simply it is like adding up the terms in a given sequence, simply. And let's look at it through example. This I showed you. I'll go through it again. How you can compute summations. Let's say this first one, part A, question A, this is given to you, and you have to compute this notation. We know that this is the lower limit, this is the upper limit, and this is your formula for finding out the terms. So you will start from here. This will be your first integer, and wherever you have k in the expression, you will replace it with first one is 1, so it will be, and then because this is sum, so you will add them up. Second one will be the integer after 1. Third one will be after 2. Okay, you will simply add them up. So it's the same thing, just that you are adding them up, and you have to reach up till the final term. So A4 till A5, like this. Okay, so this is how you can write down the sum of the terms. Okay, and then you can compute the values. Either the values are given to you in the question, or you have to compute them yourself. In this particular question, the values for each of these terms are given to you, so you can simply substitute. A1 in the question is equal to -2, A2 in the question is equal to -1, then A3 in the question is equal to 0, then A4 in the question equals to 1, and then A5 in the question equals to 2. And then you can compute mathematically. Okay? So this is how summation notation works. This is one type of question where the values for the terms are given to you. Then solution is also provided, so you can go through that. And next type of question where the values for the terms are not given to you in the question, you have to compute. So you have to start from the lower limit and you have to reach the upper limit. And you have to plug in these values of k in the formula that is given to you. For example, here the formula is k square. Wherever you have k, you will plug in, you will start from the initial value and reach till the final one. Okay, so here it will be equal and add them up. Here it will be equal to k square. So first one is 1 because that is the lower limit, square, plus after 1, what is the next integer? 2, and the formula is k square, so square. After that 3, you have to reach till the upper limit. So like this, 4, you have to reach till 5, and then you will compute. This will be, and then just add them up, whatever answer you get. Okay, so either the values for these terms are given to you, or you have to compute them yourself. Okay, these two types of questions. Then another question is that you have to write down a summation notation is given to you, and you have to write it in its expanded form. So what you will do over here is that you will look at the lower limit, you will look at the upper limit, and plug those in this formula. Okay, adding them up because it is summation. So the formula is -1 to the power I over I plus 1. This is the formula. So you will start from the lower limit. Wherever you have I, you will plug in the smallest value. So you have -1. In the power you have I value, the smallest value of I is 0. You can get that from the lower limit. So replace I with 0. Then below in the denominator again you have 0 with that. And then next one after 0, you know it's 1 in the numbers 0, 1, 2, 3, 4, right? So this. So next one you will sign will be of addition because this is summation. Next one after 0 is 1. Wherever you have I, replace it with the value plus, and next after 1 it's 2, so replace I with 2. And then you see here the final value upper limit is n. So what you can do is that after writing maybe 3 to 4 terms, what you can do is like this, because it's not a specific integer value is not given to you, it's n. So you can write it like this, and then your final term will be replace every I with n. So this is the expanded form. Okay. So 3 types of questions in summations. One is that the formula is given to you and the values for the terms are given to you. Second, this like this. Okay. So formula is given to you, values for the terms are given to you. You have to look at the lower limit, start from there, reach the upper limit and add them up. And then substitute the values. This is one type of question. Second type of question is that the values for the terms are not given to you. You have to compute yourself. Again, you will start from the lower limit, reach the upper limit, add them up and get your answer. Then third type of question is that you have to, formula is given to you, you have to write it in its expanded form, where final, a specific value for the final term is not given to you. Okay. So there you have to write it. You will look at, you will give maybe 4 to 5 first terms, add them up, and then write your final term. In between, you will have these ellipses. Okay. So these 3 types of questions. And then also you can change from similar to finding explicit formula, you can change from the summation notation to expanded form. It's the same thing. Okay. These 3 types of questions, and after that product notation, it's the same as summation, just that in this, instead of adding the values or adding the terms, you multiply them. Everything else is same. Means the this condition is same, means the upper limit, lower limit is less than or equal to the upper limit. It's the same in both summation and product. This is the symbol for your product, the capital Pi. Okay, this is the same. The condition is same. The concept of lower limit and upper limit is the same as in summation. Just what is the difference, that in summation you add up the terms and in product you multiply them. Everything else is same. Those joining so late, I'm not sure what's the problem. If you're not able to join, please check your connection. Okay, so okay, if I will answer the questions, there are 2 questions. How many should we solve if the upper limit is in? You can, for that you can provide 3 to 4 in the best scenario, 4 to 5 first few terms, and then just write ellipses and then give the final term. Okay. So this question I have answered. And second question is that you did not understand if we have n as upper limit replacement with I, because you see, you are in your let's look at let me show you. Okay, over here I will show you. See, you have the notation, right? And here is, this is the lower limit, this is the upper limit, and let's say this is the expression, for example. Sorry, this is k, if k is equal to 0. So you see in your, and you have to find out first few terms, sum of first few terms. First, let's say first 5 terms. You see, you are this is where you have to replace. So k square, okay. So you are replacing every k with some integer. All right. So starting from the lower limit. So your first term will be, you will replace it with whatever is given in the lower limit. So first one will be 0 square. Then second one will be, what is after 0? 1. So 1 square. What is after that? 2 square. After that, 3 square. After that, you have to reach the upper limit. Let's say in the upper limit, some particular integer is not given to you, n is given to you. So n is the final term. So what you can do is that you can simply write down some ellipsis and then n square. Okay. So just like you are replacing every k with the values, you if in the upper limit some particular integer value is not given to you, n is given to you, simply replace it with that. Okay. Here it could be, it could be any, it could be k, it could be I, whatever, it could be anything, any variable. That is what I mean by replacing I with 0 in your final term. Okay. Is it clear? I hope it is clear. Okay. So next we were on product notation. How do you represent it? This is capital Pi representation. Here you have your lower limit, upper limit, and then whatever is the mathematical expression or the formula. And how do you represent it generally? Start from your smallest value here and then multiply. So for multiplication, it could be, symbols could be this dot, okay, or it could be this cross, or it could be this asterisk. Same thing. This is all same. Okay. So these are different representations of multiplication. It's the same thing, so don't get confused. It's simply the product. Remember, summation is addition, product is multiplication. Okay. These two notations. Now, how to compute? Let's look at the examples for computing product. So here, first one, k, lower limit is 1, upper limit is 5, and then you have simple k. So you will start from lower limit, plug that in k. So first one is simply, it's k, there is no, it's very simple, there is no other operation going on over here, multiply. After 1 you have 2, after 2 you have 3, after 3 you have 4, you have to reach the upper limit, so till 5, okay? And then just multiply these and give the answer, okay? For this one, the formula is k over k plus 1. What is the lower limit? 1. So wherever you have k, substitute that with 1. You get 1 by 2. And then multiply it with, look at the upper limit, it's 1. You don't need. You only need 1. Okay. Because your lower limit and upper limit are same. So this will be your answer for the second question. Next, we have properties of summations and products. So there are 3 properties. First one is for summation and third one is for product. They are the same. Let's go through these 2 first, and then lastly we'll go through second property. First one is, let's say 2 separate summations for 2 different sequences are given to you. Okay, like this. So this is the summation notation for first sequence, and this is the summation notation for second sequence. Okay, this is equal to, you can bring all the values together in one notation. So lower limit and upper limit, it remains the same, and break them down as this. So first sequence, second sequence. Okay, so this is equal to the separate sum of two sequences is equal to the sum of all both the sequences all together. This is first property, and this is for summation. For product also it's the same. Means if you have two separate, let me erase this. Third property is for product, and it's the same as the summation, just the operation is different. Means if you are given two separate products of two different sequences, so this is first one, and then you can write it like this, or you can write it like this also. It's the same thing, okay, as I told you previously. So this is your product notation for the first sequence, and this is for the second sequence. This is equal to, you can bring them together under one product notation, multiply the terms. Okay, so this is the third property, just that here you have product, and in summation you have addition. Then second property is a bit different. That is for summation. Let's say you have some real number represented with variable c in notation. For example, c, some real number, it could be any real number, and then it is being multiplied with some summation. This is equal to c dot. So you can bring the real number inside and multiply it with the this. Okay, this is from your distributive law, generalized distributive law. Okay, so implement, I will show you its implementation also. These are three properties that you need to remember. And this is the same thing, don't get confused. This is the same thing as your upper limit and your lower limit, as discussed in summation and product notations. So let's say okay, for second theorem, do we multiply c with every limit or only one? I will explain that to you through an example. Let's say here you see, so you have to write these expressions as single summations and single products. So you see over here, if you remember the three properties, two of them are applicable over here. First property for summation, and second property where you have the product with the real number. So what you can do over here is that simplify this first using the second property. Okay, so keep this same for now. I'm solving part A. Okay, n, and you have, this is the summation for your first sequence, and then in second one you can simplify it by applying the second property. Okay, second property tells us that we can bring the real number inside, which is 2 in this case. So 2 into b of b, okay, like this. Then after that, this is by property 2, or you can say theorem, I think 5.1.1 in your book. So I'll show that to you as well. So here you will see 5.1.1 and property 2. Okay, and then lastly, the solution is given to you over here, but I'll show it to you. Here what they're doing is that you're plugging in the values first. So values for these sequences are also given to you. Anyway, now you have to write down these two as one summation. So a k plus 2 like this. Okay, so you just bring this down as it is, and then using property 1, write the summation notation as 1. Okay, like this. And yes, this will be multiplied with all the terms that you have, whatever you get over here, okay? Depending on the lower limit and upper limit. So this is to answer the question that is posted in my times. Who wants to switch the device? Yes, you can, and then okay, I have admitted you, student who asked for switching the device. Okay. Is it clear? The student who asked the question about second theorem, is it clear to you? Okay. Then for product, what you will do is you will simply use the third property for product, and I will write the answer over here. K is equal to M, and we have N, and then we'll have AK multiplied with the second. So third property 3. Okay. So this is the implementation of properties to simplify these given summations and products, where in the question you had to write them down as single summation notation and single product notation, and then the values for these expressions are also given to you. So I haven't substituted them over here. You can substitute them, okay, and then simplify like this. In next slide, you will see that I showed these examples to you in their original form, a sub k and b sub k, but the values for these are given to you in the question, like a sub k is equal to k plus 1 and b sub k is equal to k minus 1. So here they have substituted, so you can do that. It's the same thing, just that you are substituting. So check in the question, if these values are given to you, you have to substitute, but the properties will remain the same. You have to the steps are same. So you see over here, this is by second property, and then this is by first property, and then you can simplify this expression. This will give you this answer. So single for product again, simply substitute the values. This is a sub k, the value is given to you in the question. Then this is b sub k, and the value is given to you in the question. Apply the third property and then simplify it. So these are sum and product notations. Then we have factorial, and then n choose r. N choose r, we will look into it in more detail in your counting topic. Here, just to introduce this topic. So n factorial is, we represent it with n and then exclamation mark. What this is, that you simply multiply. If you want to find out, for example, let's look at some particular integer. Let's say you want to find out 7 factorial. How you can find that out? This is the representation. How you can find that out? You will take all the preceding integers till 1 and then multiply them. So 7 multiplied by 6 multiplied by 5 multiplied by 4, then by 3, then by 2 till 1. This will give you factorial of 7. Okay. And there is for 0 factorial, just like when we have some in the power, we have 0 that is equal to 1, whatever that number is, it is equal to 1. Similarly, 0 factorial is considered as equal to 1. Okay, so this is pre-established, so remember this. And then we have a recursive definition for factorial that will help you in your mathematical induction in simplifying the terms. Okay. So recursive definition is that we know that 0 factorial is equal to 1. So except for that, where n is equal to 0, it will be, the value will be 1. Other than that, n factorial, another way of writing that is n, you can separate the first term and then this. So you can represent n factorial like this also. This will be helpful in your mathematical induction. That is why it is mentioned this is applicable. You can separate out the first term and then take the factorial of next. I will show you an implementation, an example of this, how it works. For example, let's say, let's look at how n factorial and n dot n minus 1 factorial is the same. It gives you the same result. Let's say you want to find out factorial for 8. Okay, now this is in this form. We can write this down in this form also. So n is 8 and then you have product of 8 minus 1 because n is 8. That's why n minus 1 is 8 minus 1 factorial. So it will give you same result. What does it mean? 8 multiplied by 7 factorial. Okay, so it's the same thing. You are simply separating the first term, and this is applicable. This is a general formula which is applicable to your any for any integer, any given integer. Okay, let's look at how this is applicable over here. So if you see 8 factorial, this is the first example, this one, and 7 factorial. Now if you see, let's apply this concept. Here you see n is 8, so 8 and then you have 7 factorial over 7 factorial. So it makes your calculation easy. Okay, the answer is 8. Okay, so this is the application of this definition, means this was n and then you had n minus 1 factorial. Like this. Similarly, let's look at another example like this one, d n plus 1. Before that, let me clarify that if first value is n, then general, for example, let's say you have a number, you have 8, 7, 6, 5, 4, 3, 2 and 1. Generally, if you want to represent this in the generic form, in the form of variables, let's say you represent it in the form of n. So if n is equal to 8, what will be these values? This will be 7 is equal to n minus 1, 6 is equal to n minus 2, 5 is equal to n minus 3, 4 is equal to n minus 4 until you reach 1. Okay, so this. So in that context, we are talking about in this formula. Okay, so let's try to solve. Oh, okay. Can you hear now? All right. Okay. There was. Let's solve question number D using this recursive definition. So this is n plus 1 real and n factorial. So if we apply this recursive definition over here, the number after n plus 1 is n. Okay, and then after that it's n minus 1 and then n minus 2, right? So we can separate this term according to this recursive definition. What we can write it as n plus 1, and then after that we have n factorial. This is the second, and we can write it in the form of n factorial. Okay, and then we have n factorial over here. We can cancel this out, and our answer is n plus 1. Is it clear? Does it make sense? Yes, no? Okay. You mean factorial? You want the explanation again? Okay. All right. So I'll explain again from the beginning. Okay, first of all, do you understand what factorial is? Okay, so factorial, how do you represent it? N factorial, okay? And then let's say before that, let's say you have a sequence of numbers, for example, 6, 5, 4, 3, 2, 1, okay? And let's say you have to, when we have to find out factorial of 6. So this will be equal to this sequence, okay? Your product of all the preceding integers, including the number for which you have to find out the factorial. Now, if 6 is equal to n, because here n is equal to 6, right? So n is equal to 6, then what is 5? How can you represent it? This is n minus 1, right? And then what is 4? This is n minus 2, means 6 minus 2 is 4. 6 minus 1 is 5. Then 6 minus 3 is 3. Then 6 minus 4 is 2. And then you have 1. Okay, 6 minus 5. Right? So these are the representations of these numbers, symbolic representations of these numbers. And then you have, this is one thing. Second thing is that you can write this down as n and then n minus 1. In this context, what does it mean? Let's say you wanted to find out factorial of 6. You could simply find it by writing that down as n factorial. But you can also find it by writing it by separating the first term and taking the factorial of the remaining numbers, means n minus 1 factorial. What does it mean? That you have 6 over here and then you have n minus 1 is 5, right? When you take factorial of that, it will give you same answer. So 6 factorial, it will give you the same answer as 6 into 5 factorial. This is what it simply means. And this is the recursive, this is based on the recursive definition, which is this one of factorial. And you can apply this in finding out the values for given questions. It makes your, it's easy, it makes it easy to calculate. Okay, implementation of all this is, I have shown you by calculating the answer for question number A and then B. I will go through that again. Let's say 8 factorial. You have to find out the answer for this. Now here you can apply in your numerator. You have 8 factorial, right? So apply the same concept of this recursive definition, means n is equal to 8. And then n minus 1 is equal to 7 and its factorial. it will give you same answer, right? Just that it makes it easy if you have some 7 factorial in the numerator, 7 factorial in the denominator, and you get the answer. Okay. And then let's look at this one. D. So n plus 1, if we apply the same over here, we know that this is if you had n over here, if the number after this is n plus 1, right? So means this is n plus 1, and then next number is n factorial, so simply n factorial. And in the answer, in the denominator, you have n factorial. This is for part D. So you can cancel n factorial in the numerator denominator, and the answer is n plus 1. Similarly, for E, we have n factorial. You can separate that out. Next one is n minus 1, and then in bracket, in denominator, you have n minus 3 factorial. Okay. Or you can write it as like this. And you can and then this is just like example to show you to okay. So these are the applications of your recursive formula for recursion. Okay. So is it clear now? So it's the same thing like this one. This, and then you can simplify it. They have simplified it over here, so you can simplify. Is it clear now? Okay. Next, n choose R. So this topic is here. I'm just going to introduce you to this n choose R. In your counting, we will look into it. Where we will study combinations and permutations. There we will study more. But what n choose R is, this is how you can represent it. And usually the n is a bigger number as compared to R. And then here you have in the formulas, you have the application of factorials. For example, n choose R has, or n combination R has formula n factorial divided by n factorial into n minus R factorial. So this is just the application, just to show you an application of a factorial in n choose R. And the condition over here is that R is less than or equal to n, and it is greater than or equal to 0. So this is the range. So what does it mean? That n is greater than R, or greater than or equal to R. Okay. So this is the domain, and R is always less than or equal to n and greater than or equal to 0. Okay. There are different representations. One is this one. Then you have n choose R this representation. Then you have simple this one, and then C n R. So these are just simple different representations of the same thing. This is to introduce you to this formula, this one. Okay, the formula for that is, how do you read it? N choose R. You can also write it like this, n choose R, and the formula for that is this. Okay, here you will be using the factorial, the concept of factorial. We'll study more about, for now just keep it in mind. We'll study more about it in combinations and permutations. So this was all about sequences and different concepts in sequences. Next, the main thing that we will look at is the main topic, principle of mathematical induction. So proving statements, proving given statements using mathematical induction. So we have covered direct proof method to prove given statements, and then disproving statements using counter examples. And this is another method of proving statements using mathematical induction. And then we will have proof, indirect proof, that next week we will look at those. So in your, what is, let me go through the principle of mathematical induction first. All the things that we have covered, that are included here, we have already covered those in your predicate logic. So you should be familiar by now with this notation. Let P of n, which is your predicate, okay, predicate or property or function, let it be a property that is defined for integers n, and let a be a fixed integer. Okay, suppose the following two statements are true, this will be the base for your mathematical induction, the things that you have to show in your proof using mathematical induction. So in your first step, when you are using mathematical induction method, will be your basis step or base step. There what you will have to do is you have to prove this property to be true for some fixed integer, and this fixed integer is given to you in the question. Okay, just like in your predicate logic, you had universal conditional statement and hypothesis was given to you and conclusion was there. So similarly, this and also in your sequences, initial value is given to you. Similarly, this a fixed integer would be given to you in the question, and you have to prove this property of n to be true. Starting point will be you have to prove this to be true for this fixed integer. Then next is mute your mic, please. Second, in doing the using mathematical induction is induction. Okay, and in this one you have to show two things. You have to assume this P of n property to be true for P of k. Okay, you have to assume it to be true. And second thing that you, this will form your inductive hypothesis. And this will be important because this will be your starting point in the proof. The proof that you have to show is for the next term after k, which is P of k plus 1. Please mute your mic. So this is the structure of proof using mathematical induction. Okay, and these are the principles of mathematical induction. Let me show you through an example. And this is the same thing, you can go through it. This is the same thing that I have explained to you just now. Means your basis step where you have to show that P of A is true, A is given to you in the question, some fixed integer. Then second step is your inductive step where you will have two things. First one will be P of K, this will form the inductive hypothesis, and second one will be this you will assume to be true, and second will be the proof that you have to show actually. Okay, and without showing the proof in your basis step for this particular integer, you cannot move to the next inductive step. Okay, let's look at it through an example. So there are two examples that I have included in this in these slides to show you two different methods to show the proof for given sequence. So in the question, what does it consist of? When you have a statement that you have to prove using mathematical induction, a sequence is given to you on the left hand side usually. On the right hand side, its explicit formula is given to you. So first thing sequence, second thing formula, third thing the initial value or or A is given to you. So here A is 1. Okay, so that is given to you. These three things are provided, and then you have to show basis step, and this whole is in the question. This is P of n. Okay, in the basis step you have to prove that left hand side is equal to right hand side for P of A. Then in the second step, which is your inductive step, you have to show two things. First you have to assume P of K to be true. Okay. Then you have to prove P of K plus 1. So you have to show proof for this, you have to show proof for this. For this proof, your starting point, you will utilize your, this is inductive hypothesis, you will utilize inductive hypothesis to show the proof for P of K plus 1. These steps will remain the same, whatever sequence and formula is given to you. Steps will remain the same, just mathematical expressions and everything that will be different. Okay. Now there are two methods to show the proof. One is that you show that you compute left hand side and right hand side equally. Okay, this is first method. Second method is that you focus on, you pick one side and then manipulate it mathematically in a way that you reach the right hand side. For example, if you pick left hand side, you compute, you perform some mathematical operations, and then you reach the right hand side. Okay, you don't show them equally. The proof for that, you reach from one side to second side. So for the first one, for this example, I will show you first method, and for second example, I will show you the second method. So here mathematical, the sequence is there. This is sum of first few integers, and then the formula for that is, this is established formula, explicit formula for sum of first n integers, n into n plus 1 over 2. Now you have to prove it using mathematical induction. The smallest value is given to you, which is n is greater than or equal to 1, means the smallest value is is 1, because a is 1. Okay, so this is what you have to show the proof for first. You will start from your basis step. Okay, let's start over here. Okay, so let's start writing proof for this. So first will be your basis step. This whole thing is P of n. Basis step is you have to prove P of A. What does it mean? That you have to prove it to be true. Take from here, for you have to prove this sequence and this formula to be true, means left hand side is equal to right hand side for P of 1. How you do that? You, wherever you have n, just replace it with 1. Okay, on both sides. So you can show them side by side. Here simply it's n, so replace it with 1 on your left hand side. Then focus on n only, and then on your right hand side you have n into n plus 1, and then this, and then compute it. This is 2 by 2, which is equal to 1. So you see left hand side is equal to right hand side. This is you have proved the base step to be true. This is how you prove your base step. After you have proven this left hand side to be equal to right hand side, you will move towards your second step, which is inductive step. I will erase this and start the inductive step. So this is the first method that we are using, means you are showing the you're computing left hand side and you are computing right hand side, and then you are showing that both of them are equal to each other. Left hand side is equal to right hand side. Next is the inductive step. Here you have to first assume that P of K is true. What does it mean? How you will write this down actually? Take P of N means take this. Wherever you have N, replace it with K on both sides. On your left hand side, it will be, you have 1 plus 2 plus 3 plus N, so replace it with K. It is equal to right hand side, which is wherever you have N, replace it with K. Okay. So this is your inductive hypothesis. Mark it because you will use it in your proof, and you don't need to separate it over here. Okay, I'll just bring it closer. This is important. Next thing that you have to show in the inductive step is you have to, so this is assume P of K to be true, and then next is you have to prove the term after this, means P of K plus 1. This is what you have to show the proof for. How do you write it in this the sequence and the formula in K plus 1 format? Just look at your inductive hypothesis, and on your left hand side you have 1 plus 2 plus 3 plus K, and then plus K plus 1, next term after K, right? And on your right hand side, replace every K with K plus 1. So here you have K, replace it with K plus 1. Then you have K over here, replace it with K plus 1.
Miss, you muted yourself.
Miss, you're muted.
Who is doing that? I gave the permission, so you can the students who just go and coming back again. For those, I gave you the permission, and you are muting me. This happened before as well. That is why I didn't allow you to. And please don't do this. Or let me change the settings again. Please wait for a few minutes. I'll change the settings and then I'll resume. Can you hear me now?
Yes.
Okay. All right. All right, I'll resume. So where were we? All right, so you start from, in the inductive step, you start from the assumption that P of k is true and replace, what you do in that step actually is that you replace every n with k on both sides, and then you mark it, because you will use this inductive hypothesis, this assumption, in your proving part. Second thing that you have to show in your proof is P of k plus 1. There, what you will do is, on your right hand side, you will write down the whole sequence from the inductive hypothesis and then add k plus 1. On right hand side, you replace every k with k plus 1. And after that, because from the assumption you know that this sequence, this part before adding k plus 1 is equal to this formula from the inductive hypothesis in the assumption, so you can substitute this sequence with the formula from the inductive hypothesis, okay? And then bring down the k plus 1, this value down as it is. This is on your left hand side. On your right hand side, you have already this k plus 1, you have your formula where you substituted every k with k plus 1. So mathematically, you can simplify it. Now, after you reach this point, it's up to you how you compute it. It's what you have to do is that you have to show that left hand side is equal to right hand side. This is what you have to show. How you compute it, you have to use mathematical operations, and that's up to you. How you, maybe you can use some algebraic formulas or whatever, depending on what you get over here. For example, here what you can do is that you can make the denominator same, and then just that what we are concerned with is that you have to show that left hand side is equal to right hand side. Okay, so that is how you show the proof. And then once you are done, once you have shown that left hand side is equal to right hand side, you have shown that P of n is true for whatever is in the, you can just copy paste the statement from your question. The main thing is basis step and then inductive step. In that you have assumption and proof. Is it clear? If you want me to repeat any concept, please let me know. In the meantime, I'll give you the attendance code. This all is included in your midterm, so please, if you have any questions, you can ask me. Okay, I've posted attendance code. Please mark your attendance. Yes, you can use calculators in your exam. Yeah, yes, you can use. Yes, but they should not be programmable. The code is there. Please mark your attendance. I see 214 people, and then here I have 292. Presence. Wow. Okay. All right. Next is those who are leaving. Please, it's up to you how you study for the remaining topic. There is one topic left. Not the topic, but just one method of mathematical induction. So I have provided this proof from your book also. This is all with the explanation the same as what I have explained to you. So you can go through that and you can refer to page 280 and 281 for this particular example to see how we write proof for first n integers. Okay, if you don't understand anything, then you can ask me. And next one is how we can use this formula for first n integers to evaluate some given sequences. So let's go through that. So for example, this sequence is given to you, 2 plus 4 plus 6 plus, and you have to evaluate it using the formula for first n integers. The formula for that is the one that I have showed you just now, the proof for this. So this is the formula for first n integers, and then you have to evaluate this sequence using this formula. Okay, we know that this formula is for 1 plus 2 plus 3 plus up to n, right? So first you have to convert this sequence in this form for which the formula is actually. Okay, so this you have to analyze and then convert it into 1 plus 2 plus 3 plus up to n format, and then apply this formula to calculate it. So for this particular example, if you take 2 as common, you will get the sequence for which is your first n integers. Okay, if you analyze this sequence, you will find that if you take 2 common, so you see 2 ones are 2, then 2 to the 4, 2 3 to the 6, so you're taking 2 common, and then here you have the first n integers. Now you can apply this formula. So n will be this last value. Okay, so just plug in this value along with this 2. Okay, so 2, and then instead of this sequence, you can plug in the formula for that. N is 250, so write that down, n, and then you have n plus 1, so 250 plus 1, and then you have 2. Now 2 gets cancelled and you're left with 250 into 251, and then whatever the answer is. So this is how you can use the formula for first n integers to evaluate a given sequence. First you have to convert it into first n integers, and then plug in the you will get your n will be the final value, and then plug that in the form. You can plug in the formula. Okay, so this is the first example. Let's look at second one. Second sequence is 5 plus 6 plus 7 plus 8 up to 50. So you have integers like 5, 6, 7, 8. So there is no other pattern. It's simple integers, but you see it should start from 1. So you are missing 1 plus 2 plus 3 plus 4. These values are missing for you to apply this formula. So you need to have these values here first, and after that you can apply the formula for first n integer. So let's see how we can do that. So this is the sequence. Add the values to get the sequence, original sequence. Okay. And then minus these values, because your original, when you compute it, it should remain the same as what is given to you over here. Okay. 1 plus 2 plus 3 plus 4. And now you can plug in this formula. N will be this final value, So plug in the formula, which is n into n plus 1. So n is 50. Then again you have n, then plus 1 and 2. And then you have this part minus 1 plus 2 plus 3 plus 4 is 10. So this will give you 50 into 51 over 2 minus 10, and then you can compute it. Okay. So this is how we analyze the given sequences and convert them into the original sequence, which is sum of first n integers. Whatever is missing, we add that, or if we can take common, we do that, and then we implement the formula, plug in the values, and then calculate. And then you can also write down the closed formula for a given sequence using the formula for first n integers as a base. How? In the third example, if you see here, you have to write this sequence in its explicit formula form. Now, if you're using first n integers as the base, so you see the sequence is same. You don't need to convert or do anything else. So you have 1 plus 2 plus 3 plus, the final value is h minus 1. Just take this first n integer formula, and this will be n. So replace every n with h minus 1. Oh, sorry, you also have this h is greater than or equal to 2. Okay. Then you have h minus 1, and this gets cancelled, so h, and then 2. This is h. Okay. And this is the closed formula for this sequence where you have used the formula for n in first n integers. Okay, so this is how you can use some given formulas to calculate some sequences like question number A and B, or write down the closed formula for a given sequence. Okay. We are left with one more sequence. It's the same, just one method is left. Here I will go through it. Let's say you have to show the proof for a geometric sequence, and that is given to you. Okay, I will explain it to you. Now, the first method that we used to prove prove a statement or a sequence and its formula using mathematical induction is that you show both left hand side and right hand side. You show the computation for that. Second method that I told you about was that you start from one side and then you take some steps, you reach right hand side. So in this second example for the formula of sum of a geometric sequence, here I will show you the example, the proof for that. So yeah, okay. So let's say this is what you have to prove. This is for the sum of geometric sequence. Okay, this is your left hand side, and this is right hand side. Here R is some real number and it is a constant. And here smallest value is 0. Okay, the same thing, your base step will remain the same, means you have to show it to be true for p of 0. What does it mean? That your left hand side, wherever you have n, replace it with 0. And on your right hand side also. sorry, r r minus 1. Okay. And we know that wherever you have power 0, it means 1. Okay, so you have shown that left hand side is equal to right hand side in the base step. Now, so this is the same as in your previous example. In your inductive step, we will use second method. In inductive step, again, we have two things. We have the assumption part, which is your inductive hypothesis, and we have the proving part. So first you will write your inductive part as it is, your assumption part as it is. So this is the second step after basis, inductive step. In this, first you have assumption P of K, which is this replace every where do I show? Maybe I can, okay. Replace every n with K. Okay, this is your inductive hypothesis. Now in your proving part, it will be a bit different. Okay, so what we will do is we will take the left hand side. First we will write it in the form of K plus 1, K plus 1, and then R. Replace K with K plus 1, so you get K plus 2, because 1 plus 1 is 2, minus 1, or minus 1. So now what we will do is that you can take any two sides. We will take left hand side, and we will take some steps such that we reach right hand side. So we will not do anything with right hand side. We will manipulate left hand side to reach the right hand side. So this is the second method. Okay. How? Here you can use the concept that we studied in factorial, that you can separate one term. Okay, and this is based on your recursive definition. So we can do the same thing over here. And for example, we can separate K plus 1. When we separate K plus 1, what we are left with is whatever is present in your inductive hypothesis. Okay, so how we can write it after this to reach K I is equal to 0, and then we are left with this, right? And then we are simply replacing, separating, or we can say I0, like this. And then we know that from the inductive hypothesis, we know that this is equal to this. So substitute it. Bring this down as it is. Okay. Now when you simplify it mathematically, you will get this. Okay. So you are not doing anything on the right hand side. You are simply manipulating using the concept from your sequences or other mathematical expressions and all, your principles, rules and principles, properties, whatever. It depends on the type of question you have. This is also a trial and error process. It will help you when you practice. So you can use that and focus on one side, and then take some of those steps, some mathematical steps, and then reach the right hand side. So whichever you find easy, that's you can apply that method and show the proof. So doesn't matter. The main thing is that you show your base step and you show your inductive step. In your inductive step, in your base step, what you show the proof for P of A. A is present in the statement given to you in the question, which is usually the smallest integer. Okay, or whatever is given to you, it's given to you in the question, so you have to read the question carefully. This is in your base step. Then in your inductive step, what you have to show is two things. First, you have to show the assumption, And this will be same for all types of questions, just that you will be replacing every n with k. And second thing is you have to show the proof. Proof for what? P of k plus 1. For proving, you can use two methods, two types. You can use either of the two methods that I have explained to you. Means you can show calculation for both sides, or you can focus only on one side and then take mathematical steps to reach the other side. Okay, so that's up to you. And then the details of this geometric sequence, because we have exceeded the time of the lecture, so I'm not going to go through each step, but I have included that in your slide, so you can go through these and also refer to page 282 and 284, fifth chapter, sequences, mathematical induction and recursion, and try to understand. If you still don't understand, main things I have explained to you, but you still don't understand, you can ask me. Lastly, we have the application, just like we have the we can use sum of first n integers, its formula, to evaluate some given sequences or write down closed formula. Similarly, we can use this formula for sum of geometric sequence. This is the formula. We can use this to write down the closed form or closed formula for given sequences. Again, we have to analyze the sequence. Okay, so for example, first one is, this is your first sequence. I told you that R, in the geometric sequence we have R is the constant, any real number. Okay, so here R is equal to 3, and then we need to, because we need to have, in the geometric sequence we need to have R, so we need to identify R from the given sequence. And then the second thing we need to identify is n is the power in your final term. So n is equal to m minus 2 in this particular example. Okay, so what you will do is that you can write this down in the form, this sequence down in the form of this formula. Replace every R with 3, because in this particular example it is equal to 3, and then n with m minus 2, because in this example n is equal to m minus 2. So, and then from the formula you have plus 1 also. Here you have R, so that is equals to 3. Okay, then simplify it. So this is the closed form for this sequence. Then for the same goes for second one. Here first you have to convert it into the sequence for geometric sequence, which is this. This is the geometric sequence. So first you have to convert this whole sequence in this format. You need to have 1 and you need to have R. So I will just give you a hint that how you can get this sequence. If you take 3 as common, 3 square as common, you will get your sequence. Okay. Now you have the sequence, geometric sequence, and then you can apply the formula over here. From here, you will first see what are the values for R, because that is what you need. So R is, you see, this is the constant. So R is 3, and then you need n. N is the power in the final term, which is here again it's m minus 2. And then just replace this sequence with this formula, and you will bring this down as it is, because it is part of the sequence. And then you have 3 and m minus 2 plus 1 from the formula, minus 1, and then you have 3 minus 1, which is 2. So it is equal to, you can simplify it, 9, 3 3 is 9, and then you have 3 minus 1 minus 1, and then 2. So this is the closed form for second sequence. So it's the same thing, that first you have to convert in the sequences and then apply the formula. So that's all for today. So we have covered we have covered two main topics: sequences and mathematical induction. In sequences, we have looked at what we have looked at. We have looked at what the components of sequences are, terms, and how to the lower limit, upper limit, and then some notations, summation and product, then their properties, and then how to use those properties to simplify given notations, and then factorial and n choose r, and after that also using all these concepts in examples to calculate for calculation purposes, and then mathematical induction, where we have looked at two examples. One is proving for sum of first n integers using mathematical induction, and second, proving the statement where you have geometric sequence using mathematical induction. Two methods for your proof of P of k plus 1. One is that you show the calculation for both sides, left hand side and right hand side by side. And second method is that you focus on one side and then take some mathematical steps to reach the other side and then show the proof for that. Okay, and your mathematical induction, what you have is two main things. You have your base step and your inductive step. In base step, you prove the property for smallest integer that is given to you in the question. So you have to look at the question to find out for P of A to see what A is, and then prove that in base step. And in your inductive step, you have to show two things. First, you have to show the assumption, means P of k. So you replace every n with k and show that, and then you show the proof for P of k plus 1. In P of k plus 1, you use your inductive hypothesis, which is P of k, to start writing your proof. Okay. So, and then you can also use these formulas to evaluate some other sequences given to you, or you can also use them to write down closed formulas for other sequences. So that is what we have covered in today's lecture. If you have any question, you can ask me. Otherwise, we will conclude. The student who could not mark the attendance, sorry, I cannot generate the code now. It can be generated only till 4 p.m. till the class timing. Midterm exam will mostly be conceptual because it is MCQs. So conceptual questions from your topics, propositional logic, predicate logic, all this will be posted on my times also, and exam will be during your lecture class timing. So for you, it will be from 2 to 4 p.m. In your regular lecture time in week 9. Okay, so for the other section, it will be during their lecture time in week 9. And propositional logic, predicate logic, you can look that up in your MI also. And mathematical induction, and then direct proof, disproof by counterexample, set theory, these are included. You will find them in your MI, but I will also post them on my times. Exact date, this is week 9, I think it makes 22nd of November. So we are in week 6, 7, 8, 9. So for you, Friday class, it will be in week 9, 22nd of November, from 2 to 4 p.m. Your lecture class time, you need to be present in the venue because your attendance will be marked manually. So those who I don't get the slip, the attendance slip that I will give you during your midterm exam, they will not be considered as present in the midterm. Okay, so you have to be present in the venue. All this explanation will be provided to you on my times. It will be posted on my times soon. Please don't worry. Just check my times from time to time. It will be posted over there. Everything will be posted again over there. Okay. Definitions, yes, definitely, because it's your MCQs. So you need to know everything. Definitions, the conceptual questions, and all those, because you will not be calculating anything. There will be no short question and answers. Yes. Any other questions?
Hi, Miss.
Yes.
Just wanted to ask, this is for the group assignment.
What? Sorry. What?
This question is about the group assignment, and
Which
my
one?
group is doing task 2 for it, the one
Okay.
that has to deal with medical supplies and patient data.
Yeah. Yes.
For task 3, where it says that we need to get the minimum spanning tree by using OpenStreetMap and Kaggle. Do you know exactly how to get the minimum spanning tree? Because when I go on OpenStreetMap, it's only an editor.
You first thing is that you don't necessarily need to use OpenStreetMap. You can use any other source also. This I explained in your last week also, that you can use any other source as well. Second thing is the scope of the area or location that you are covering. It's up to you. You have to define the scope. Third thing is that minimum span to find or to draw the minimum spanning tree or find a minimum spanning tree, there are different algorithms. Example of one algorithm is given to you in the explanation of the task, but you can use any other algorithm as well. I think this algorithm that is given to you, but you can use, there are certain like Kruskal's algorithm, there is Prim's algorithm, so you can use any of those. So that is part of your exploration in this assessment, that which algorithm you find suitable that answers your task properly. Okay, so that is up to you.
So we need to make our own minimum spanning tree based on the data that we get.
It will be specific to your data set. Yes.
Yeah, so we need to make our own minimum spanning tree with its weights then.
Yes, and you have to show that when you look at the graph, of course, you can find the minimum spanning tree just, visually when you see, you can find it, but you have to show the implementation of discrete structure concept, which is the algorithm, application of algorithm to find the minimum spanning tree. So you have to show all that, you have to integrate that calculation in the content of your task.
All right, and then next for the task 1 and 2, I believe that asks for patient data. When I was talking to another group that had the same task as my group, same case study as my group, they said that when they went to ask you about it, that some of the data needs to be real data, and if any other data needs to be added on, it can be redundant. That's what you said, apparently.
Not redundant.
Sorry, not redundant, but
you
dummy
can add to
data.
it. You can add to it, but all of the data set must not be, it shouldn't be dummy. It should be based on, you have some data based on, you explore the patterns in the data that you have that is available to you. But if you find it to be less in amount, then you can add more to it. Look at the pattern, what you find in the available data, and based on that, you can generate some dummy data, but not all of it. You have to, then you have to explain.
Yes, that's why I'm a bit confused for this task, because the task 2 for the one that's asking about clinics, it's asking for patient details and patient appointments, which I don't think that's allowed for just public use. I don't think you can get real data for that. Most of it would be dummy data, no?
If it's like available, then if it is available online, then they take permission. Otherwise, the columns that I have mentioned over there, like opening hours and then vehicle availability, that you can find. For example, some groups they couldn't find online data set, open source data set. So what they did is that they looked at the physical facilities around some maybe where they are living or other areas, and then they went on to the websites. There they could find the opening hours, and of course patient specific data, it will not be available exclusively, but the other things like opening hours and ambulance availability, that they were able to find. For some, they were able to find. For example, if they found 20 hospitals or clinics, for maybe I think 11 to 12, they could find the ambulance availability or other columns that are mentioned in your task. For others, they couldn't. So there you can fill in the gaps. So this general information will generally be available to you. So you can use this approach. If you don't find it in the open source datasets, you can also look into some hospitals where you are living around that, and you can search them up, their websites. There, usually it will be available to you. And also, it's not necessary that whatever columns are mentioned or data points are mentioned in the task that you adhere to only those. You have the freedom to maybe remove one of them or add something else that is relevant. So you have freedom over there.
Okay, Miss. Thank you for the information.
Yeah. Okay. Welcome. Any other question? If no more questions, then we will conclude today's class. Midterm review. Actually, week 8 is your independent learning week. So even if we have a review class, it will be online, but I cannot confirm it because it's your independent learning week. You will not have classes, and then in week 9 you have the exam. No more questions, then we will conclude. Welcome. The dataset depends on the task. So if it makes sense, you can use, but you have to justify. You have to provide all the details. Yes, there will be questions from all the topics that are included in your midterm.